Okay, good morning, everyone. Good afternoon, and welcome to Biomass Canada Cluster webinar series. My name is Mahmoud Ebadian. I'm a research associate at the University of British Columbia, working on biomass, bioenergy, and biofood supply chain and logistics. I work with the Biomass and Bioenergy Research Group, as well as Forest Product Biotechnology and Bio Research Group at UBC. Today, we actually have the last webinar from our webinar series, which focus on de-risking and commoditizing underutilized biomass resources to facilitate the evolving Canadian bioeconomy. As you probably know, and if you attended the previous webinars, we already had 8 webinars. And each of these webinars focus on one project as part of the Biomass Canada cluster. And today we have actually the last one for this webinar series, which is again focusing in all of this webinar, we have focused on different aspects of using agriculture biomass for low carbon intensive bioenergy, biofuel, and also value added bioproducts. And today, actually, the presentation is going to be focusing mainly on using agriculture biomass for value-added bioproduct. Just a quick background on Biomass Canada cluster. This is a cluster led by the Biofuel Net Canada network with the financial support from Agriculture and Agri-Food Canada's Agri-Science program. And also we have contribution from industrial partner for each project. The main focus again is agriculture biomass, and this cluster is trying to identify the different potential application for the use of underutilized Canadian agriculture biomass for again different application, including bioenergy, biofuels, and bio-based products. And the cluster has 10 activities, and each activity is looking at again improving or developing technologies for either production of biomass, like pre-processing, improving the quality of biomass, and also looking at the logistics of agriculture biomass and distributing in a cost-efficient way for different applications. So that's the focus of the cluster. Just before we start the presentation, a few housekeeping items. This webinar will be recorded, and at the end of the webinar, we have a copy of the recording and also the presentation slide on Biomass Canada cluster website. You can actually access to not only to this webinar, but also to all of the last webinars. So you can find actually 9 presentation and also recording of all of the webinars since December we started this series. We have 2 boxes, Q&A, so please, if you have any question, type your question in this Q&A box, and then at the end of the presentation, we address the question. And also, I encourage everyone to type your name and affiliation in the chat box so we know who is actually attending this webinar. Before I introduce a speaker, I just want to mention that we are actually working on the second round of webinar series for 2021. But this time we are trying to actually invite a speaker from outside of Canada. So they talk about the experience, successful stories of using agricultural biomass for different applications. So right now we are talking to different consortium and companies in US, in Brazil, in Europe, that they have, in India, in China, that they have actually experience of using agriculture biomass for different application. At the moment, we are talking to Agro Bioheat Consortium. This is a consortium based in Europe, and they are actually promoting the use of agriculture biomass mainly for a small scale heat application. So please, if you have not registered to Biomass Canada cluster newsletter, please do so you can actually get update about the new cluster webinar series. But we should start. We are planning to start that in May. So just keep in mind that if you are interested to attend the future webinars, we should have some of like new presentation again from international perspective of using agriculture biomass for different applications. Okay, with that, it's my great pleasure to introduce the speaker for today's webinar, Dr. Animesh Dutta. He's a professor and a director of Biorenewable Innovation Lab with the School of Engineering at the University of Guelph. He's specialized in advanced energy system and thermofluid science with hands-on experience in reactor design and pilot plant operation, design and performance of various tests in laboratory scale and pilot scale units, thermal design and process development. He has published over 260 scholarly works, including 140 referred journal articles, 110 conference proceedings, and 19 technical reports. His current research focuses on resolving critical engineering barriers for new sustainable technologies for utilizing waste and renewable resources in industrial scale. His research is focused on thermochemical conversion and characterization of biomass and waste for energy, chemicals, and materials, and design and optimization of advanced energy systems. So with that, I asked Dr. Animesh Dutta to start his presentation, and we are looking forward to hear your presentation. Please take it away.
Thank you, Mahmoud, for a nice introduction. And definitely, without further delay, let me go to the presentation slide. So I'd like to thanks audience for attending the webinar today. So what I'm planning to present in next 27 slide is on transforming low value agri-food processing waste to high value chemicals and materials. And it is a combination of work done by my group, especially my all masters and PhD students who are working tirelessly. So I'd like to thank them before starting this presentation. So let's start with the one. I would like to start with acknowledgement, definitely Canadian Agriculture Partnership for the funding, and the biomass cluster holder Biofuelnet, and my industry partner who are supporting this project, the four from Ontario. They are Cinder Power Development, Custom Steam Solution, Stream Canada, and IGPC Ethanol. So the ultimate goal of this project, and especially our work, is to produce a wide variety of renewable products, including that's biocarbon, so that it can replace coal, renewable chemicals that's generated from the petroleum or oil waste, and biomethane to replace the natural gas, and biofertilizer from mainly non-food sustainable agri-food waste, which currently we are throwing it off for landfill and other resources. So we are trying to use that waste as a resource for our application. And the reason for us, we would like to meet Biomass Canada's cluster goal in three ways. Number one, we would like to valorize those agriculture and food waste and crop residues, mainly greenhouse and food processing waste. And we would like to develop green processes and also propose defined product value chain based on our research. Ultimate goal is to strengthening the sustainability and bioeconomy of Canadian agriculture and agri-food sector. So as I mentioned that our role is to waste is a resource, and that's we are focusing on. If we look into the waste around and by waste, they are abundantly available. Currently, we are throwing it off or using it for landfill. And most importantly, they are renewable. And if we can use them, they are carbon neutral. But more than advantage, they have more disadvantage, and they are very low energy because of the very high moisture and light and very bulk density. So it's very difficult to transport them off. And they have very high moisture content, which result to very low again and energy. And biomass as well as agricultural waste, they are fibrous in nature. So when they are fibrous, if I want to grind them or make them a small particle, for example, to use fuel in pulverized coal-fired boiler by pulverizing it, very difficult to do so. And the most important part, this biomass, especially a lot of agricultural biomass, has a very high ash content, and in terms of mainly high alkali and this, and they possesses a lot of problem when you want to combust it in a combustion system, by promoting agglomeration, sintering, and sometimes corrosion. So we need to overcome those parties. So hence we can say that agricultural biomass is not regarded as an ideal replacement for fuel and material. So we must need to do something to use it. So we are proposing a processing method. We call it hydrothermal processing or hydrothermal carbonization. So hydrothermal carbonization able to convert a wide variety of biomass, especially those who are in has a lot of moisture, because hydrothermal carbonization uses when treated biomass in hot compressed air instead of drying, something like pressure cooker. So we cook it in the water. So if the biomass doesn't have much moisture, you need to add water. So this is ideally suited for biomass that has a very high moisture content. And it usually run at the temperature of, let's say, 180 to 260 degrees Celsius for a temperature of 5 to a couple of hours and so. And is able to produce three stream. The main one is the hydrochar that we are focusing on, and that hydrochar can give us some unique morphological properties, and it also produce liquid product. We call it hydrothermal processed water in the order of 35%, and very little gas, which is mainly CO2 in it. So beside hydrothermal carbonation, there are other steps also we use is for conventional pretreatment, something like drying, torrefaction, and pyrolysis, some thermochemical conversion process. Now let us see in terms of their feedstock properties when a biomass has a more moisture content and ash content, how these two behaves, especially if it is a conventional drying and torrefaction. We need to remove all the moisture in it, so need a lot of latent heat of energy, so may not be ideal and is a very energy intensive. Compared to hydrothermal is favorable given that it work on the water. And also in ash content, when we try to remove the ash, you know through hydrothermal, we should be able to do that because we can have leaching effect and they take the alkali content from the hydrothermal. Alternately, we cannot reduce the ash content through either drying, torrefaction, or pyrolysis. Also, in terms of processing time, when biomass and wood kind of biomass, we know that is a kind of a inert or low mass transfer and heat transfer through this surface. But when you are imported in the water, it enhances the heat transfer and mass transfer. So we can have much lower processing time in for hydrothermal conversion. In terms of energy intensity, if the biomass is very high moisture, drying is not favorable, but we need to investigate the energy requirement for hydrothermal conversion. And definitely in operation, drying, torrefaction, and conventional pyrolysis are mainly suited because they have been used in operation, but hydrothermal may need some challenges. So our goal in this project is to produce biocarbon, and that should have a unique morphological properties that and also produce some liquid water. And we would like to establish the different value chain, and that our value chains that we like to establish based on a number of research questions. So the research question that we like to through this project looking into, can we produce this industrial grade biocarbon from this low quality biomass of agri waste, which has a very high alkali content and very low heating value and very poor grindability, so that the alkali content will be low and we can have more heating value and pretty high grindability. Also, can we be able to produce a higher value product, something like activated carbon and biocatalyst from this hydrogen? And the industrial grade biochemicals that we produce through hydrothermal processing, can we be using? So based on this, so we develop a number of hypotheses. So our one hypothesis is that if we change the processing conditions, something like time, temperature, feedstock sizing, we should be able to generate a biocarbon that has a various morphological properties. So we can tailor make the biocarbon depending upon our application. And hence that should able to eliminate a few key barriers that agri-food waste system currently processing. We also hypothesize that we should be able to process it for activated carbon biocatalyst, probably through different activation and other processing. And the third important one, that when we produce processed water, there has a processed water has a, high acidic content, something like acetic acid, so their pH is low. So if we integrate it with anaerobic digestion, where in anaerobic digestion, hydrolysis is the main rate limiting factor, probably these two have a synergistic benefit, will help eliminate the case limiting factor for anaerobic digestion, and at the end will yield the high biogas generation. So in order to do this hypothesis, we'll establish two things. One, we would like to develop HTC process design and development for doing this research. And then we'd like to feedstock processing and characterization for both, and also process design and in product design based on the different application, and ultimately characterize those products. And number two, we like to also see the life cycle assessment to see some of those indicators of this. So I'd like to show in a nutshell what we have done, especially in the biocarbon. So what we did, we have tried a wide variety of, starting from the woody biomass to construction waste to purpose grown biomass to agricultural biomass, definite and wet biomass, tomato vines, even industrial waste to produce biocarbon. And this biocarbon that we produce could have different application. For example, could be used for the soil amendment, could be used for the heat and power, could be used for the metallurgical application, and wastewater treatment. So in one case that I want to present here, so we look into the miscanthus as a biomass here in this graph. If you look into, so this was our miscanthus here, and this has a very low heating value as 18.5 megajoule. If I would like to compare with coal, which is about 25.8 megajoule. And also if I would see their grindability, miscanthus is very difficult to grind as it is in raw form, but in order to coal, easy to grind, so one can use for the pulverize coal-fired boiler. So what we try to use both dry torrefaction and hydrothermal carbonization. In the dry torrefaction, we are able to generate up to 21 point, increase the heating value depending upon the temperature. We have gone up to, in this case, 280 degrees Celsius for 30 minutes. And then when we try to grind it, we were not able to produce very low particle size of grinding. But in hydrothermal, we are able to produce nearly that is similar to the coal, especially the heating value, we reach up to over 26 megajoule, which is in the bituminous coal range, and the grindability also nearly similar. So, and the reason for hydrothermal to have this good grindability is because when we do it, the bond and the lignin cellulosic bond, they break down and make it easy to grind. And one of the important things we have seen that the ash that we have able to reduce the alkali content, both potassium, sodium, and phosphorus in this 30 to 70% up to the range. So we can conclude that especially this hydrothermal pretreatment can be an ideal pretreatment to remove some of those barriers. And definitely depending upon application, we may need to further processing. Now let's start with our first case study. In this case, the first case study, we try to develop something based on the circular economy concept. So in this concept, we look into the Ontario corn field. So we look into the corn that will produce and the corn residue. And in this corn residue, here we use corn residue first hydrothermal process. And that hydrothermal process 1, we're able to produce the biocarbon and then liquid. So the biocarbon, we characterize it and get the energy value out of it. And the liquid, we has use it for the anaerobic digestion to produce biogas. And that biomethane also, we quantify the energy value it. And the liquid that we characterize it for the fertilizer or nutrient recovery, something like nitrogen, phosphorus, potassium, and ammonium. And our hypothesis is that that can be used for digested or for land application. So in this research, we have used hydrothermal characterization based on 200, 220, 240, and 260 at 3 times like 10 minutes, 20 minutes, 30 minutes, and a number of configuration, and use design expert software. And then we able to find a good value, especially at 240 degrees Celsius as 30 minute processing time, able to give us an energy recovery value of 79% from the raw biomass, and also able to produce this nitrogen, phosphorus, and K value between 20 to 30% recovery. And this paper is published in Energy Journal, especially in 2008. So based on this economic concept, so we are proposing a kind of a community-based concept here, where waste to wealth, a circular approach. So we are hypothesizing that the lignosulfuric biomass can directly be used in a hydrothermal carbonization to produce hydrocarbon and liquid product. The hydrocarbon can then be used in a CHP, combined heat and power, and heating can be go to the greenhouse, or some heating can go to the rural community. And the liquid can be anaerobically digested to produce biogas and fertilizer. Fertilizer can be used for the greenhouse, for the food, and the biogas again methane for the remote community. And the food waste that's generated by this or greenhouse binds from the greenhouse as well as remote community can then be again go back to the system for the further treatment. So in this closing loop approach, we should be able to develop a kind of a sustainable approach for a community, for example, for the northern community, for example, in this case. So we thought this be an approach, and we would like to even evaluate it using life cycle analysis, a part of this concept. So the next slide, what I want to show a kind of a configuration of life cycle analysis process that we published in journal Process in 2020. And in this case, we took about 2 scenarios. This uh, first scenario is the left one here, is a direct combustion method. So in this scenario, what we did, we use the biomass, and then that biomass, if it is wet, we dry it. If it is dry, we don't directly use it in the boiler for combustion, then produce steam and generate power. So this is our baseline scenario, which is. And in the proposed scenario, what we did, we integrate hydrothermal carbonization and anaerobic digestion. And when we use hydrothermal carbonization, we produce hydrochar, then we burn it in the boiler and produce electricity. And from the anaerobic digestion, we produce biogas and use it in for the gas turbine cycle to produce the power. Then we have done a lot of sensitivity analysis based on different data, and data that we collect either from literature review or from the experiment. And we have developed these two just simple diagram here. If you look into this very far left one, it shows moisture content versus efficiency. So it says that if hydrothermal, the blue one is the HTC AD scenario, and the red one is the direct combustion scenario. So the direct combustion scenario is better if we have a feedstock that has a very low moisture content. The moment we have a moisture content, let's say over 40% here, then the hydrothermal AD system is a preferable choice. Similar thing can be seen from the heating value. If I have a very low heating value fuel, definitely hydrothermal AD system is better. But if I have a very high value biomass, then direct combustion is better. So these kind of analysis definitely help us to select and to choose a pathway, right pathway, which option to go. So we have tried to develop this one. Our next analysis is based on something that's biorefinery concept from the corn corn processing waste. So this biorefinery approach that we are showing here is we can have any non-lignocellulosic agri-food waste, and this non-cellulosic agri-food waste can be fractionized, and from the fractionization we try to evaluate the different component. One is protein component and biochemical component. And if there is any toxic material, our proposition is to go for hydrothermal carbonization that can produce biocarbon and ultimately can use absorbent or fertilizer. So in this case study 2, what we did, we use the feedstock from low grade corn distillate solubles, especially that we get from IGP ethanol, and sometimes they have is uh, contamination as like written as alpha toxin contamination. So they are looking for new value addition, especially they produce about 16,000 metric ton annually of this one, and currently they're using animal feed. Now when the contamination, this cannot be used. So based on the our biorefinery approach, what we did, we separate this one for protein fraction as well as for the biochemical fraction. And the key result is that we found lipid soluble leucine and proline in protein fraction that could provide future scope for antioxidant peptide, and the glutamic acid in the protein that we got here can be used potential for ACE inhibitory peptides. So these are the certain things that we are able to identify in from these low value low grade condensate materials. In terms of biochemical part, we have listed here that's the highest value, and we also found that the higher content of aromatic pyrrolate compound from the protein fraction, and trypsin generated peptides that had also found high bioactive components. So these probably can be used for the further analysis and so on. So this is what we identify from these low values. And in terms of chemicals, we again go into the further details. We found these three items, glycerin and butanoic acid and 2,3-butadiol as a highest component, and this can be used mainly for the industrial paint and plastic applications. We have further used analyze the peptides for the protein, and in this way we have used uh, response surface optimization method, and we have able to concentrate dependent plant or different antioxidant activities in protein hydrolyzed and in molecular weights, and major alkalis generated peptides are identified with antioxidant activities here in this area. So the significance of this antioxidant protein hydrolyze and peptides could be used in for feed application. So these are most important part that we are able to even identify and quantify, especially from low value uh, corn core product, that is CCDS. So this research that's peptide research are published in these journals, and if there is any important, definitely one can look into it for the further details. So the next case that we look into is again biocarbon, especially for our research, and we try to see the CDS and corn fiber that we get from the ethanol IGPC ethanol production, if we can develop some uh, high value biocarbon out of it. So in this research, we have used again hydrothermal carbonation process, and we try to characterize those it for the different potential chemicals. And we have done it mainly from 180 to 300 degrees Celsius. And the product that we characterize for the ultimate proximate analysis, heating value, thermochemical analysis, FTIR, and again PyGCMS, PyGCMS, and PyGCMS and scanning electron microscope. Also, liquid product we have quantified using GCMS analysis and for total organic carbon. As can be seen from here, this is our corn distillates product here, and these are our corn fiber. And we able to this corn distillates and fiber from here, and it's able to bring it here. And this is a very interesting scenario here. These are not following the typical rule within the Venn diagram diagram. The reason is that it has a pretty high hydrogen content. And that hydrogen content definitely will signifies that it could be it will have a very high heating value, and the hydrogen heating value can move up to about 34 megajoule per kg. And also this carbon fiber content or hydrogen content, we are able to get pretty high nitrogen value. And those who are working in this activated carbon or carbon for energy storage usually use nitrogen for uh, embedded to increase the conductivity or electrical potential of this energy storage system. So we thought that maybe this kind of hydrocarbon or hydrogen will have the potential even further activated for high energy, high value application. So what we did in this case, we developed a tunable approach, and in this tunable approach, we produce activated carbon from this corn fiber one, and then in this corn fiber one we approach three. One we try to do directly activation, and the other one is hydrothermal then activation, and the third one is catalytic hydrothermal then activation. So we try to analyze these three approach, and the ultimate goal for this approach is that we want to produce high value activated carbon in these two steps. And here what we see that in this approach, uh, catalytic HTC, when we use the catalytic HTC with ferric chloride, slightly increase the degree of carbonization relative to uncatalyzed HTC, and also is remove a little bit nitrogen content and increase the porosity. And this carbon that we got, we further characterize using TGA, FTIR, SAM, and for nitrogen analysis. And our two-step process in this case able to produce a surface area of 1220 meter square per gram compared to 780 for direct activation method. So this approach, even tunable approach, shows that we should be able to produce high value activated carbon with much higher potential for supercapacitor application. And this paper now under review in SES Journal of Omega. In another approach, based on that, we try to enhance the different potential. We look into the miscanthus and Swiss gas application in iron and steel industry. Those who are working in iron and steel industry, we know that they are one of the main contributor from the greenhouse gas emission due to considerable amount of. So in iron industry, we need coke and as a reducing agent for iron oxide to iron metal, and also we need coal for heating. So we try to produce this iron from this Swiss gas and miscanthus, and we show that the raw materials properties in this one Swiss gas has a carbon content of this one, and they have a ash content of fairly high. And when we do torrefied, it further increasing it, not able to reduce it. But in iron and steel industry, we need carbon that has a very low alkali content, and we need to ensure that part. So in that condition, we use the hydrothermal carbonation, and we are able to reduce the ash content from very high to pretty low temperature, and we also increase the carbon content. So what we hypothesize that if we integrate the two process here, especially hydrothermal carbonation followed by the pyrolysis or slow pyrolysis, we should be able to produce a biocarbon that would have a morphological property similar to the PCI coal used in iron industry. So this is the type of PCI coal used in iron industry that has a heating value of over 32 megajoule and ash content here and a carbon content. So by doing this approach, integrating it, we are able to produce a biocarbon that gives the heating value and all those things similar, even ash content much lower. So in our approach, what we did, we first try to reduce the ash content, maximize. So we identify that at 200 degrees Celsius, the ash content at 30 minutes time, ash will be the lowest. And then we further carbonize it for the 30 minutes at 400 degrees Celsius. Then we are able to produce a coal that's similar to the PCI coal. So in this two-step process, integrating both hydrothermal with pyrolysis, we are able to have the synergetic best benefit out of these two. And that's able to give us a good value. So based on this hypothesis, we know that in iron steel industry, they need a lot of biocarbon. For example, about 1.6 million ton per year, even in Canada. So only woody-based biomass is not sufficient. So they are looking into the agricultural based. So our proposition for that meeting, using the biomass and cut it, producing the hydrothermal carbonization first, and produce, and that can go to the biocarbon for the after doing the hydrothermal carbonation and can be used for the blast furnace. So in this way, integrated HTC and slow pyrolysis of high ash and low grade biomass can be have a morphological formalities of PCI coal, and they also shown in our research as a good combustion behavior and can partially replace fossil fuel carbon and reduce greenhouse gas emission. In the last phase of our work, we try to even further develop some biocatalyst out of it. So here, what we look into this, we look into a new application, a new insight for the future design for the composite, which published in Energies in 2020. So in this research, we look into, we take this catalytic hydrothermal method to harness cranberry pomace from, especially we got it from the fruit ODR company, as a potential bioenergy and hydrogen sources. The physical and chemical properties of this, we examine it, and we were determined by the design expert system. In this study, we suggested that we should be able to develop a catalyst. If you look into the zeolite based catalyst, it has some potential benefit and some potential negative. The most important one, zeolite based, they have a high surface area and they have more microporous, but they don't have mesoporous. And that's resulting there is some coke formation. On the other hand, hydrogen has a Lewis acidity, multifunctional, and they have a more mesopore structure. So if we are able to develop these two together, we should be able to, limit some of the challenges by creating meso and micropore into the structure of zeolite, increasing the number of accessible active site for the macromolecules, and that result in enhance the thermal stability of zeolite and creating a 3D interconnected structure using activated hydrogen. So there's follow up this result recently published in a chemical engineering journal work, where we have synthesized our work. Uh, and we have also shown that this zeolite based composite using a simple one-step hydrothermal liquefaction process, and our SAM analysis, as you can see from A, B, C, D, in the so that biochar matrix in A, and in B we can see the zeolite. In C we can see 3D composite, and D hydrochar zeolite interface and EDS analysis of zeolite. So this one will be able to develop and analyzed using porosity, surface functional groups, total active site using a scanning electron microscope morphology. So this should be able to in a way next step that we are looking into now mainly focus on matching the physical and chemical properties of this synthesized composite with different catalytic process, including product from petroleum, chemical, and biomethane and alternative energy application. So then we try to develop based on that, and to say the hydrothermal carbonation is one of the most important things. So develop a continuous hydrothermal. First, we try to see what is the energy required for the hydrothermal carbonation. We develop mathematical model that is published in energy journals, and using this, we are able to use predict the temperature. We are able to predict the temperature here. So we are able to produce the power, we are able to produce the temperature in this one, and that's published in energy journals. And we show that our mathematical modeling shows that for a well insulated, sealed, and continuous reactor can decrease the power consumption significantly when aqueous phase is recycled. And the developed model can potentially be the first step in designing industrial reactor for hydrothermal conversion of biomass, which may attract the investor and policymaker for commercial application. Then with this, we develop a bench scale one, and we have shown that the continuous HTC is favorable due to the enhancement of the primary carbonate suspension, because when we use in a batch reactor, we put the biomass and we try to heat it up to operating temperature, but in continuous, the operating temperature is there and biomass exposed to that hard condition. So one can expect much faster conversion and faster, better characteristic. So with this, we also develop a continuous reactor currently, which is under commissioning, and the capacity about 50 kg per hour. So if we need a bigger one, we can go for modular. Let's say 10 module will be able to process 500 kg per hour of this biomass. So currently we are commissioning this one. So another one I want to show you a little bit, that we are also working on the gasification. So one of the most important gasification techniques that we are doing is for hydrogen production from biomass. So in this one, we employed a dual fluidized bed system, and in one fluidized bed, the calcination reaction of limestone is converting calcium carbonate into calcium oxide, and in other reactor, calcium oxide during the gasification process absorbs CO2 that originated from the gasification to produce calcium carbonate. So the end product will have much lower carbon dioxide. So one can have a highly hydrogen enriched gas. And we have done it, and it's recently published in Energy and Fuels. And in this one, interestingly, we use two stream of waste. One is especially we use eggshell as a source for the calcium carbonate instead of the limestone, because we found that eggshell has about 97% calcium oxide. And we use this, and we show that, we demonstrate that without eggshell, with steam gasification, we probably maximum can get 40% conversion of hydrogen, but that's go up to over 75% with the presence of eggshell when we capture the CO2 out of it. So the utilization of eggshell and in gasification, definitely eggshell and gasification has been experimentally investigated, and that has a huge potential using two different waste stream from the agri-food sector, can generate and produce hydrogen and this gas, making the hydrogen production as carbon negative from the biomass. So in conclusion, we are able to preprocess any kind of feedstock and produce biocarbon, and that biocarbon we demonstrated either through gasification, through conversion, uh, or producing biocatalyst, or producing activated carbon, and that has a huge potential. And the liquid, we are able to show that we are able to produce some agrochemicals out of it, and some peptide protein, even biogas, and biofertilizer. So we show that the waste that we generate today is cannot not only the waste, it's a research and just waiting for a application or further investigation to produce what currently we are using for our based on our fossil fuel. Even we have demonstrated that this hydrogen can be used for the electrodes or supercapacitor and can produce very high surface area carbon, biocarbon. So with this, I would like to thanks, and I want to thanks my whole team. So I am not mentioning anybody's name. This is a team about 17 people, and a few are not there also. So they have contributed immensely in order to what I have presented today. And right now, I think 11:45. So I have about 15 minutes time for discussion. And floor is yours, Mahmoud. Thank you.
Hey, great. Thank you very much, Animesh. Great presentation. Lots of great application for agriculture biomass, different pathways, different application. Thank you very much, Animesh, for sharing such an informative presentation with us today. So we have about 15 minutes for Q&A. So I encourage the attendees. I'm sure they have question for Animesh, but I'd like to start the first question, Animesh. So you showed different application for the technology that you are basically actually developing the HTS process. What are the main barriers? As you saw that we have actually possible application for different, like for steel industry, for energy application. Do you think in Canada, what are the main barriers right now that we cannot really use these processes in commercial scale? So we can actually use agriculture biomass?
This is an excellent question. Actually, I also asked, and Don is here. Maybe Don probably able to answer in better way. But I can tell you a few things. Uh, when I try to see the gas production, uh, again we cannot compete with the cost. That's for sure. Even activated carbon, Ontario. Just give an example. We are importing 100% activated carbon from US and other parts of the world. Even though it is not difficult, we can produce it here for the wastewater and the treatment here without any problem. But whenever I try to, it's easy to buy it, and that is, is available and is cost effective in order to create a new market. So there's kind of, I don't see incentive yet there from the provincial sector or whatever sector it is, just to penetrate. However, we have all the resources, we have everything, we have the know-how. But the thing is that even it is found, import is much cheaper than the in-house production.
Okay, so it's mainly economic barrier, not
I would
really
say that
technical.
is the mainly economic, especially for the activated carbon. In for other processing, definitely for the hydrothermal technology maturity is not there. So because hydrothermal carbonization, even Europe, they are a little bit, they are ahead. And but feeding of biomass, which is the fibrous and all those things against pressure in a continuous process, is the very difficult task. Because you have to make it, grind it, paste it in a liquid form, then use the positive distance pump to do those kind of things, okay, to process it. So that is another barrier. And the subsidy, that's probably is not sufficient. Probably the amount of subsidy we give to the fossil fuel is much more than what we try to give something in the biosector, much lower. Alternately, the biosector, if you put $1 subsidy, you get much more cleaner job. Whenever fossil fuel based, if you put subsidy, you create just technical because know-how is there. But in biosector, you use local economy, local resources, and create a much greener job.
Yep.
And all those things. So probably it is, I'm not sure here, because our decision making people, policy making people can look into when they give the subsidy to the fossil fuel versus renewable biomass, to look into that effect, whether we are trying to create greener job, clean job for the farmers, for the local people, for the local community, or we want to give something for the technical job for a known established source.
Okay, thank you very much. So the next question is about the scale. So do you have a scale in mind for commercial application? I guess the question is about the HTS process that you're developing.
Yes, this is another fantastic question. Especially, we look into the pressure and a kind of off-the-shelf material, because we can make a custom one. So currently, the one that we build, it is a off-the-shelf material, a kind of 8-inch diameter tubes, and that can hold up to 50 kg, per hour processing condition. So what we are proposing here, if I have a modular of those, I don't know in a greenhouse how much they produce waste. Let's talk about they produce, or in a community 500 kg. They want to process it. So you can have 10 of those modular setup can produce 500 kg per hour process. So in a way, this is the world. That's what we are looking into in that kind of demonstration phase right now.
Okay.
But if you increase the diameter for the pressure, same pressure, you need to increase the thickness. Drum, yeah, technology is there, but whether do we want to increase the cost of no? Because the moment you go big, whether a farm can be able to handle that much cost or not. So this economics and scaling is a really hand to hand based on the application where you want to have it. So our approach, we want to have a agriculture farm-based system, because that's the focus of this Biomass Canada cluster, and we look into the farmers first, especially at this stage.
Okay, great. So a follow-up question, Animesh. So you're looking at a small scale farm application. So if a
That's right.
farmer produce, let's say, biochar, how they can't distribute it? Imagine we have lots of farming locations. So are they going to pelletize it? How do you see the distribution system if they want to send it to a larger scale facility?
So in the closed loop approach that we hypothesized, we see that because there is something people they want for nutrient recovery. So if you have a biocarbon with a good surface area, so even in a greenhouse, the water that goes, you can capture some of the nutrient that's taken flash away from the water, and you can use that carbon into the soil. And you know that sometimes carbon in the soil for the soil amendment, that can be one of the options. They can in-house use it. Alternatively, they can use it by burning it or doing gasification, their own requirement for heating in the winter. Or if the farm in a rural community, they can supply a little bit like a distributed generation. So this is one approach. And the other one is centralized approach, and you are working on the logistics. Definitely, we need to do the pelletization and all those kind of logistic in line with that. And we found that when you have a hydrothermal carbonization, they have some extractive, which is a kind of tarry, kind of gluey type. So you don't need any other binder. This will act as a cell binder. So you can have a very good, high quality, durable pellet. So we did even test the pellet by throwing it from the 6 foot several times to see whether it is retaining their shape or not. And 97% time it retains its shape.
Okay.
It's a pretty durable pellet.
Okay.
I want to produce.
So I guess even the next question is sort of related to that. I think you already addressed it. Can we pelletize material prior to feeding into the bioreactor?
Yes, actually, definitely, it's very easy to pelletize it. Because we have tried even raw biomass, and you know that you need a little bit binder, or the moisture and the heating is needed. Even in the dry torrefaction, is even further difficult. When hydrothermal, because it's cooking under water, and you just dry it natural dry, but it has a kind of a tarry kind of material in it, extractive, that helps gluing by itself. Easy to come.
So you talk about the yield. I remember you showed the percentage.
Yep.
So can you sort of again mention the yield you get for different pathways, like 1 ton of biomass, how much biocarbon you get, how much the liquid you get?
So this is another one is a kind of a hypothesis we say processing condition. So the processing condition can be any time between 180 degrees Celsius up to for biocarbon 260. So if you go 260, probably you can expect a hydrochar in the order of 45 to 48%. And in 240, you can over 50, 55 in that order, 60%. Okay. So this is the kind of a typical value. And the rest mainly goes to the liquid. So the liquid will have around 35% carbon in it. So when you have a liquid 35% carbon, then you can anaerobically digest it and produce the methane out of it. So the gas has only 2%, 2 to 5%. So some of the oxygen, inbonded oxygen that you have within the biomass can react with a little bit produce CO2 mainly.
Okay.
Very low, very low.
Thank you, Animesh. Another question is about the fractionation. How much fractionation of the material is needed before feeding to the bioreactor?
Well, we are not fractionizing it. You don't need to. But if you talk about the fractionation of the, corn fiber or corn distillates, I'm not sure which part you are talking about. If you talk about a biomass, you can carve it in 1 inch cubic size, no problem. You can put it in the water. That's okay, as long as you are able to feed it. The question is, in a continuous process, how do you feed it? If it is a batch process, you put it a bigger size, no problem. Is because heat transfer is very fast because it's cooked under water. So heat transfer coefficient is much faster instead of But if you're talking about the fractionization, especially for the CDS or carbon fiber, so we try to use first protein enhancement. I think we able to increase the protein enhancement from 35% what people to up to 68% for our process. But fractionation is important to know different ingredient, protein as well as chemicals what you have in this. So we use different techniques to fractionize it.
Okay.
But for the hydrothermal carbonation, you don't need to, as long as you're able to feed it.
Okay. Thank you. So next question is about the smell in the process. Does the process make any smell, and if so, how it can be handled?
Well, any kind of conversion process make a smell, but the thing is that this is a thermochemical process. So a smell is a little bit of tarry type, not the sway slash or those kind of things, and are biochemical type. So it's about when you increase the heat, that can be, but it's not that much. For example, when you burn it, combustion, you don't get much smell. A little bit of smoke. Pretty, the moment the things that you do barbecue, that's kind of a smell probably you may get.
Okay.
So
great. Thank you very much, Animesh. I don't see any more question in the Q&A box, but fantastic presentation. I really enjoyed. I learned a lot of actually potential application and also the technology you're developing. And I wish you all the best actually to commercialize the technology that you're developing in your lab, and also the students that actually are helping you to develop such a amazing technology that we actually need new technology to deal with agriculture biomass because of all of those quality issues we are dealing with ag biomass compared to woody biomass. So thank you very much for the great presentation, and also all of the attendees for attending, and also for a great question. As I mentioned in the beginning of the webinar, we are planning to have the second round of webinar series. Again, most likely we're going to have the first webinar in May. And we are talking again to different groups outside of Canada to share the information and also the knowledge they have in terms of using agriculture biomass for different applications. It's not only bioenergy and biofuels, but also value-added product we can produce from agriculture biomass. So thank you very much, and have a great day.
I also thank you, and I see the Dawn. Thank you very much for this opportunity, and thanks to Biomass Canada and AgriFood Canada for the funding. Looking forward to seeing you soon. Thank you.
Thank you very much, Animesh. Have a good day.
Okay. Bye.